好，各位老师、各位同学，大家好啊！听完刚刚王教授精彩演讲，我们今天还有第2场演讲，另外一位吴俊杰老师啊。那我们今天很高兴请到吴俊杰老师，台大大气系的吴俊杰教授。那我在这边稍微为大家简单的介绍一下吴老师，他是1986年台大大气系毕业的。然后呢，1993年他在美国麻省理工学院得到博士学位。然后呢，他在毕业以后，他就到普林斯顿大学 GFDL 做博士后研究。从93年到95年啊，所以吴老师他在国外留学的时候有一个非常完整、非常扎实的学术训练啊。那他在95年就回到台大大气系担任教职，从副教授到目前已经是正教授啊。那吴老师呢，他的著作非常非常多哦，几乎每年都有很好的文章发表在一流的国际期刊上面。那算是我们台湾气象界研究非常杰出的一个年轻的科学家。那最近这几年呢，我想大家可能都知道，吴老师他要主持一个DOTSTAR 的就是投落送的这个计划，就是用飞机飞到台风那个地方去丢投落送啊。那这个研究的结果呢，对我们台湾的台风的预报有很大的影响跟帮助。那另外也成功的让我们台湾这一块在台风的研究上面有登上国际的舞台啊。那所以我们今天非常非常高兴的请吴老师来跟我们演讲。他今天讲的题目就是跟DOTSTAR的一个方法，就是我想应该是要决定要在什么地方丢早上，因为茫茫大海要怎么选那个地方。我想我们首先用热烈的掌声欢迎吴老师。
先谢谢Working， 谢谢廖主任，还有谢谢系上王国英老师的邀请。那很荣幸有机会隔了3年之后再到系上访问。那也刚好我们今天双节来演讲。那我今天要跟大家介绍的题目呢，是叫做 Targeted Observation， 是策略性观测。那这个名词不晓得对各位同学来讲熟不熟悉？所以我先问一下，意见调查一下，大概有听过说什么叫做策略性观测的，请举手好吗？不要客气，所以我们有几位知己在下面，那没有关系。那我希望说，透过今天的介绍之后呢，能够让大家知道我们是怎么来思考这个问题。所谓的策略性观测，大概就是说，我们在做一些特殊的观测的时候，是要找到关键的地方去放资料，而希望这个资料可以达到最有效的 impact。概念是这样。那要怎么去找到这些什么叫做最策略性或最敏感的地方呢？那是有一些方法可以做的。那我今天事实上不是要跟大家谈说我们在怎么搞飞机，而是在讲说我们在要搞飞机之前呢，我们要怎么去做这些决策？那是有一些气象的理论基础在里面的。好，这是我的重点。那这一个追风计划，英文叫 DOTSTAR， 是有机会成型，也是要感谢很多国内，包括东大的，包括林佩莲老师等很多人，还有王新勇老师的支持跟协助。那当然也有很多国际的合作，在这边有稍微列了几个我们合作的一些国际的人士。那今天的报告呢，有部分是截至我刚好在1个月前在 Costa Rica 的一个叫做 Sixth International Workshop on Tropical Cyclones 里面的报告，所以我就在这个基础之下跟大家做报告。不过刚刚因为有老师跟我提到说，这个系上都目前非常的进步，都希望说学生是用英文来演讲，所以我在接下来的部分我就用英文来跟大家做介绍。So here is the outline of my talk. I'll give you an overview about the idea of the Drug Wind Sound programs and DOTSTAR. DOTSTAR is the acronym of 追风计划. Then I'll talk about the background of targeted observation and the ideas about sensitivity and adjoint sensitivity. And
since all the internationals are not here.
Yeah, that's all right. Yeah, I'll quit anytime. So we'll try halfway and see the response. So the key in the program of DOTSTAR is to develop a new scheme for targeted observation where we code Adjoint-Derived sensitivity steering vectors. And this will be the focus of today's talk. And I'll show you some of the results of our study. And in the end, I'll talk about some issues of concerns and specifically about the recommendation from the IWPC 6 meeting and related to the section about the targeted observation. So to give you an overall background about the idea of doing a new observation, here is a very simple illustration of how we can improve our understanding and forecast of tropical cyclones. Basically, we need to have better understanding about the dynamics of the tropical cyclone system. And this can be done through two separate directions. One is about to improve the dynamics of the model, and the other one is about the initial condition. And I'm sure that people here are all very aware of these issues. And about the dynamical parts, and there are some very important topics or so-called hot topics going on right now about the multi-scale interaction. That means the interactions from the convective to the eye wall, to the synoptic, and to the large scale, and even involved with the feedback of the climate system to the tropical cyclones. And on the other hand, also it is very important to know more about the air-sea interaction because the hurricanes or the tropical cyclones, they get their energy from the ocean. And because of the strong stress the hurricane exerts on the ocean surface, there's a strong interaction between the two fluids. And finally, about some of the boundary layer effects, especially for this area like Taiwan, terrain is one important issue. On the other hand, about the initial condition, and the key is how we get the best observation, and that can go into the data assimilation system and eventually improve our initial condition. That eventually can help to improve our understanding of the whole hurricane system. And talking about the new observation, this is very expensive all the time. So it is often asked, what are the most cost-effective measurements? And what are the aided values of each new observation? And these all need to be addressed and explored well before we take any new observation. So let me go to the next slide again by showing that, again, so we want to improve our understanding and our forecast of tropical cyclones. So other than the models itself, we also want to improve to have a better, accurate representation of the initial condition or the meteorological variables. And of course, these variables are from the observational data or from the data assimilation that use these data. And for hurricane studies, there are several potential sources for data. The traditional one, the so-called drop wind song, the satellite, and radar. And some of you here might have heard about the talk from Professor like Qin Yonghua or Chen Suhua about the use of the satellite data for tropical cyclone study. Yesterday we have the international colleague here. And also the radar component like from Professor Taishi Chen and also Liao Yuqing. So, but today I'm going to focus on the drop wind song data component. This doesn't mean that these other data are less important, but I'll first focus on this part, but eventually, in the end, I'll talk about the overall data problem. So let me first review the ideas about the surveillance programs using the drop wind songs. Actually, it took about 15 years of work from the US, of the Hurricane Research Division of NOAA, to conduct 20 experiments in 15 years to demonstrate the important use of the drop wind song data and their impact to the tropical cyclone forecast. And in the end of these experiments, in 1996, Bob Berkeley et al., they published a paper in fact showing that the average error reductions in some so-called ensemble model forecasts can be improved by as much as 16 to 30%, up to 72 hours, with the use of the dropping sound data. For these reasons, starting from '97, the HRD, they began to operate, they procure a G4 jet flight, and then they do the observation, they call surveillance missions operationally for all the hurricanes that hit West Atlantic area. And a series of works and papers has been published by Ederson and et al. In recent years. This is the picture of the jet. So, and these papers have been showing some very interesting results about how these new data improve the hurricane track. So now let me move on to talk about the DOTSTAR. So starting from 3 years ago, with the support from the NSC, we initiated this DOTSTAR program. And the idea is this is the first programs done in this area to use the jet aircraft to do a systematic study about using the drop wind sound to take the extra observation in a hurricane environment. And so whenever any storms approaching these areas, we would make some decision and send the aircraft out by releasing the so-called RB93 drop wind sound. And we can take the measurements of the vertical sounding of the environment around the tropical cyclones. And eventually these data were designed to be transmitted to Weather Bureau and worldwide in real time, and eventually feedback to all the forecasting centers worldwide. And so by this design, we were able to get the optimum and maximum use of the data from the international community. So we have been very lucky with all the support we got. Up to this year, we have flown 24 missions with 20 typhoons, with 29 flight hours, and with 386 drop wind sound released. So actually, the figures here shows all the tracks of the storms where we have flown, and the black squares here indicates the center of each storm when we took the observation. And indeed, for all these 24 missions, actually 18 typhoons affecting Taiwan, and actually also some of them eventually affect China or Japan or Korea or Philippines. And so this study or this observation has actually making some impact to the East Asia areas. And however, not only for the operational use of these data, people want to ask, so what is new about DOTSTAR? What can we learn more scientifically from DOTSTAR? And today, we have tried very hard to address some of the very pioneering research issues from DOTSTAR. And today I'm going to talk to you about just one issue, about targeted observation in DOTSTAR. So now let me move on to talk about a review on the targeted observation. So for those who may not be familiar with targeted observation, so here is a very quick review of the information. What means adaptive or targeted observation? They are basically the same thing. It's the observation with the target in the sensitive regions where if you can reduce the initial conditions uncertainty in those sensitive areas, you get better chances of decrease your forecast error. On the other hand, as very well reviewed in this recent article by Ralph Landman, and it's the targeted observation is an active research topic for numerical weather prediction. And it can be used for plans of the field programs such as DOTSTAR and tests of new observing systems. For example, any of the new satellite deployments, it's better to do some type of targeted observation study before you launch any new equipment like the satellites. And also application of the new concepts improving the predictability and data assimilation. And there are also a number of, actually a series of issues related to the adaptive observation. It's first about the observation types. observation density and variables and their errors. You need to know that. And also, we need to know the uncertainty, the magnitude of the uncertainty, and how they fit into the data assimilation system and how they grow in time. And to give a more review on this is also the presentation I reviewed in IWPC 6. I categorize all the targeted observations now being available into 3 types. The first type I call it dynamics-based strategy. Singular vector or adjoint sensitivity or potential vorticity are all this type of strategy. Basically, the dynamics from the model decides the strategy. The second one is, I call it uncertainty-based. Basically, you use, for example, some of the variance of the ensemble spread from the model systems. You can use those information to derive where the sensitivities are. And finally, I call it dynamics and uncertainty joint-based strategy. And actually, I think this is the ideal one because you use both the modeling information and also the uncertainty information. And what I will show later on about the ensemble transform Kalman filter and the recent singular vector based on the variance would depict this kind of the third situation. So with all this background, so I'm going to move on to talk about the history of the development of all these techniques. Actually, all the above techniques I just mentioned, they did not evolve until late 90s, so it's not very far from now. Only 10 years ago, the scientists started to develop the objective targeted observation techniques, which means in old days, we do all the new observation by subjective methods, which has no dynamics or so-called statistical basis. It's by experience, but which can be very wrong in many times. So we need the objective analysis strategies. And these can be used to test the intrinsic predictability of the models and also to identify sensitive areas, as I mentioned a few minutes ago. And the first experiment designed to use some of the targeted observation techniques starts from 1997. It's called FastText. And later on, NOPEX. And 2 years, that's 98. And then 1 more year later, the Winter Storm Reconnaissance Program. And all these 3 programs are designed to test the targeted observation techniques for winter storms. And none of them are for tropical cyclones. So tropical cyclones, the research on tropical cyclone in the old days has no specific targeted observation techniques. So let me move on to the next step. Ooh, what did I do? Yeah, wrong button. Oh, good. So starting from just 3 years ago, and several objective methods have been proposed and tested for the operational surveillance missions or field experiments for Atlantic Hurricane Studies by HRD, as well by the DOTSTAR for Northwestern Pacific Typhoons by myself. And right now, myself and Edison, we are one of the few people nowadays working on this problem. And it is to use all different kinds of targeted observation techniques to design our flight experiments. And the schemes we use now include 5 components. And in today's talk, I will focus on the one I developed. It's called ADSSV. It's called Adjoint-Derived Sensitivity Steering Vector. But nevertheless, I'll just briefly touch upon all other methods because in the end, I'll talk about the comparison of these different schemes. The first one is about ensemble variance. So obviously, it's based on the uncertainty estimation. So the most sensitive regions for new observation would be the location where the ensemble spreads from the 10 members of the unset GFS ensemble shows the most spreads or most variance. And those are the areas we identify as the sensitive region. And in this case, they generally occur somewhere around the tropical cyclones because tropical cyclones are they are the area where you make the maximum wind, so you have the most of the wind variance. The second method is the combined statistics and dynamics. It's called ensemble transform common filter. And actually this is a very unique scheme. It's basically based on the data assimilation theories. And they use the 40 members of the ensemble variance information from also the unset GFS forecast. And they use that to calculate the reduction of the analysis error covariance by any feasible deployment of the new observation data or the dropping some data. So in other words, they identify regions where if you have any extra new observation, you can reduce the forecast error covariance. By that, you reduce the uncertainty. So you improve the forecast. And there's another way to do it is so-called singular vector, which is shown here. And we do have two kinds of singular vector. One is developed by NORCAS. So the singular vectors, we know from the linear algebra that it is the region where, if you know the region with the leading singular numbers or the leading eigenvalues, where the associated singular vector will show you the location where it can maximize the total perturbation energy at the verification time. And on the other hand, the Japanese also has this similar version of the singular vector, but it's based on the moist dynamics, so it's even more complete. So with all this background, now I'm going to talk about the ADSSV. Yeah. The reason I developed ADSSV, for one reason, is actually because I feel that I'm under the pressure because I'm leading a very expensive program. I thought that we should have some original scientific ideas of our own, not only using other people's. And under that stress, I thought very hard over the last few years to come up with this very unique scheme to study the sensitivity. The idea is that I thought that the EPKF or singular vector products that I discussed earlier, they were all generally, to study these, you need to know the norm, the base of the norm, which is generally defined as the total connected energy I mentioned earlier. And there is a tendency that the high sensitivity would appear around the storm region because the tropical cyclones with very high wind around its center would tend to have the maximum energy. So, and we thought that can be very misleading. Those are may be very suitable for study for extratropical cyclones. But for the tropical cyclones or hurricanes, typhoons, I think the relevance of those products might not be related to the steering flow of the motion. It's not clear whether they are related. The sensitivity only shows you what areas will lead to the maximum growth or the intensity change of the hurricane, but not the motion. But however, we know that our current knowledge is not able to predict very good hurricane intensity. So using this method to define the sensitivity would be very dangerous. So let's go back first to talk about how do we define the sensitivity region that can really lead to the dynamics of the hurricane motion, because that's the first order of things we want to solve for hurricane forecasting problem. And the theoretical work actually on determination of the targeted observation strategy for improving the hurricane track prediction has been very lacking in literature, as I just mentioned. There's none at all before. So during the progress of DOTSTAR, we proposed a new method to try to solve these issues based on the adjoint sensitivity, and I'll talk about that in a few minutes. The idea is to define some appropriate response function that can represent the hurricane's motion, and therefore we can calculate how these response functions are sensitive to any initial conditions when we want to take the new observation. And we also wish to design some very simple parameters that can be interpreted with various clear physical meanings. And so now I'm going to show you the new work. So first, for those not familiar with sensitivity, what means sensitivity? So it's very straightforward. For meteorology problem, we want to know what input in the initial condition through the models, they were very sensitive to affect the output of the model. If they are very sensitive, we say they are sensitive. But it is very difficult to define the sensitive by this way. Traditionally, we call direct sensitivity. You just keep changing your initial conditions and see what's the response of the output and see how sensitive they are. But because with the tremendous dimensions of freedom in the model variables, it's impossible to do all the tests. So you can only try this direct sensitivity test by your physical intuition. But this is very inefficient. But there's another way to do this through the dynamics. You can actually estimate the sensitivity of the model output with respect to the input based on the adjoint model. And this has been presented back 10 years ago by Erica at NCAR. So the idea is, because if for any response function, I'll remember this particular terminology, response function, that is the issue where you are concerned about for the physical system you are interested. It is a function of the model output variables. You want to know if for certain particular outputs, for example, hurricanes tracks or hurricanes steering flow in the end of the forecast, you want to know what initial perturbation may affect this output. In other words, in mathematical form, you want to know the gradient of the response function to the initial variables, which is x in. X is a huge column vector showing all the variables of the model. And we want to know what is the R, the x in. But this is very difficult to do because x in is only R is only a function of x out. But we know x out can be related to x in through the model. So you have to do some approximation to derive that relation. And some of you here, for example, Professor Suha Chen must be very familiar with this issue. So the idea here is you have to develop your tangent linear model first. You linearize the model first. So originally the nonlinear model says the output of the variable is the input variable operated by the model. So this is a very huge matrix. And now you want to say, you linearize the equation by saying any small change in the output would be any small change in the input versus the gradient of the model. And we call this part as the capital N, tangent linear model. And with some mathematical manipulation, and you can derive that. Through the adjoint model. So the adjoint model in its mathematical form is the transpose of this huge matrix. So the relation we got here shows that if you know the gradient of the response function to the x out by operating on the tangent on the transpose or the so-called adjoint of the tangent linear model, you can derive this. So now we are going to start all the calculations. And the system we are going to use will be based on the MM5 adjoint. But this can be applied to any other types of model as long as you are able to derive its adjoint form. So I'm going to show you two studies about how this whole thing works and how they affect the results. So, and we will choose two DOTSTAR cases for our examination. One is about Typhoon Mary, the other is Typhoon Minduli. Some of you might still remember this. And so these two are all storms in 2004. And this is one of the storms where the model was making some impact. The data, without using the drop wind zone data, the unset global model was showing a pretty bad track forecast. And it got improved by more than 50% in errors after the use of drawing some data. So we'll use this as one case. On the other hand, there is another case that the Miniarity case, we see that there is somewhat improvement and somewhat degradation at different time of the forecast. So that means the data is not showing very significant improvement to the data. So now with this background, I'm going to show the results about the targeted observation of ADSSB. So the idea is we need to run the forward model in time for up to 36 or 48 hours to get the so-called basic state of the model based on the nonlinear model. And so you can get the output of the model. And we call this is the verifying time. You want to know if this is the starting observing time, if any of the new observation at this time can improve the forecast of the hurricane track at this time. And so after running the forward model by 36 hours or longer, whatever, and we do the inverse integration, which is called the adjoint model integration backward in time. So for all the integration based on the backward integration, we use the -0 up to -36 hours back to the observing time. So the goal is to identify the sensitivity areas at the observing time that will affect the steering flow at this time. We define the steering flow here, and we want to know how this steering flow is sensitive to the areas in this time. So first, we need to find out, we use the box as the verifying area, and this is a very typical use for hurricane study because we know by taking an average flow, you filter out all the hurricanes' strong azimuthal wind. By that, you can estimate the hurricane steering flow. So we use the box to calculate the model predicted location of at the verifying time. And we define the response function as the U component of the steering wing and the V component of the steering wing. And of course, the area and the vertical integration can be varied depending on what kind of hurricanes you want to look at, though, and it can be shown that these are not very sensitive issues. So we define the R1, R2 as the steering flow at the verifying time. With that definition, we can do the further calculation. The first, we calculate the sensitivity of the output of R1, which is U component to U. And actually, at the -0th hour, it will be identical to 1 in the box. That is, by definition, has to be so, but 0 elsewhere. On the other hand, the R2 degree will be 1, but 0 elsewhere, and the cross term will be all 0. But because the UV information is not very intuitive, so we create another variable, which is with, because we know that the relative vorticity is function of U and V. So we can use the RDU and the RDV to calculate the RD vorticity, because vorticity is easier to understand. So, and with more mathematical formulation, we can derive based on, because we know the UV, the vorticity and divergence are basically an operation on U and V. And by applying some of the fundamental linear algebra, we can derive the RD vorticity and the RD divergence based on these equations. But of course, we have to solve this Laplace equation, and then we can derive the RD vorticity from the RDU and the RDV from its three-dimensional structure. So with that, we are going to talk about the RD vorticity. This means what is the sensitivity of the U component of the steering flow 36 hours later to the initial vorticity. That's this kind of pattern. Why? If you increase any of the vorticity in this direction, this is the positive means you increase the U component of the wind because the vorticity has this kind of circulation. On the other hand, this will be negative because any increase of the vorticity here would reduce the steering flow. So with the both of these dipole patterns, we started to do the calculation. They would evolve in time during the backward integration. And how these patterns change depends on the physics of the model. So the model, the basic state of the model decide how the patterns would evolve in time. Eventually, we will find where the sensitive regions are 36 hours beforehand. So so what I mean here shows that these regions shows their high sensitivity to the hurricane motion 36 hours later. And this will be the observing time. So let me also show you the example of also the R2D vorticity. In this example, we show that the V component of the steering flow is even more sensitive to the vorticity field. That's here, very high, much higher here. So, but this is still too complicated. So I decided to make this choice by deriving, I define a new vector, it's called ADSSB, as the vorticity sensitivity, the R1D vorticity and the R2D vorticity as a vector. So with this vector, this information gives us the idea about the magnitude of the degree of sensitivity. The magnitude of this vector shows the sensitivity. And the direction here shows for every tiny change of the vorticity, where the steering flow will be directed, the change would be. And let me show you one example. This is the result. So at the -0 hour, this is the verifying time. These are the ADSSB, and they evolve in time. Eventually, we found that the motion of tropical cyclone at this time is sensitive to this region at the observing time when the tropical cyclone is here. So in this case, it is very sensitive to this area, to the northeast of the tropical cyclone. In general, generally speaking, these are the regions where we might want to take extra observation if you believe this result it can be trusted. On the other hand, because UV determines the vorticity, also the divergence. So we also need to calculate the sensitivity to the divergence. And what we found here is that the value here is much, much smaller. Let me show you the comparison here. The sensitivity to the vorticity is much higher here. It's about 1 order magnitude higher than the sensitivity to the divergence field. So, and we have demonstrated that, actually we have done further analysis by doing some so-called non-dimensional comparisons, because we want to be fair for the comparison. And we show that these are indeed less important and negligible. So in the future, I'm going to focus only on the vorticity field. But this is physically very easy to understand because most of the large-scale flow in our atmosphere is controlled by the vorticity component of the non-divergent part of the wind. Therefore, our large-scale steering flow must be more sensitive to that than to the smaller flow field. So this is the final product. So basically, here we show the sensitivity to the observing time with respect to 12 hours earlier and 24 hours earlier and 24 hours later, 36 hours later. We found that all during the following 12, 24, 36 hours, the sensitivities are all located in these areas as shown in this diagram. And we also found that most of the sensitivities are located right at the edge of the 700 hectare, the edge of the Pacific height. So here we appear to demonstrate that the sensitivity has something to do with the age of the Pacific height. That sounds also pretty consistent with our intuition. And so let me further demonstrate this by another example. This is another example, it's called Miniarity. In this case, the model is very close to the actual track. The error is very limited. And we also found that the sensitivity are in these areas. at the edge of the subtropical high again for this particular case. But please take a note here that in this case for Miniarity, the drop zone was released right here, and it happens to be within this region of the high ADSSB. And we also found that this happened to be the case that our data are showing higher impact. On the other hand, in this case, the data are not deployed here because these sensitive regions are way far away from the storm, and we were not able to fly into that area without specific design of the change of the design of the program. So to save money, but we actually couldn't get this right. And indeed, in this case, the data is not making much progress to the improvement of the forecast. So now, maybe I'm going to talk about 3 other new issues, which is very important when we talk about this adjoint sensitivity. First, when we do the derivation for adjoint, we have to assume the so-called linear assumption. So we have to demonstrate whether the linear assumption is valid for tropical cyclone study. That is very important. The second, we have to demonstrate actually the adjoint model, when I use it, it was originally designed by, when they do the backward integration, they neglect the moist component. So that's a dry physics for adjoint. So what is the impact of that dry physics? And thirdly, we have to demonstrate the exact impact of this sensitivity. So I'm going to show that by, remember, here I put 2 locations here. This is a location where, as you can tell, with very high sensitivity. And this is a point, equal distance from the storm, but to the south. This is to the northeast, but this place has almost no sensitivity. So keep this in mind, and I'm going to show you the impact study. But before we do that, we also need to demonstrate the vertical structure of the sensitivity. This is also very interesting. And the idea here is we make 4 different circles at different radii from the storm center at 400, 600, 800 to 1,000 kilometers away from the storm center. So we unfold each ring of the radius. So, and we want to look at the cross-section of that sensitivity in vertical cross-section. And it can be demonstrated here. What we found from, this is 400 circle, and so we unfold the circle. So this is south, west, north, east, south. So there's a circle there, north in the center. So we can identify that right between about 500 and 700 hectares. So it's middle level right here. And about 600 to 800 kilometers to the northeast of the storm, we find a high sensitivity. And this is we are very sure this is right at the edge of the subtropical high in the Pacific. And in this particular example, we show that it is the strength of the subtropical high determines how they might affect the storm motion. And this is again very consistent with our physical intuition. And of course, it also extends further out to 1,000 kilometers, but not very large in the near the storm center. So this is a very unique study, and you can also see how the vertical structure of the atmosphere affects the hurricane motion later on. With this background, so maybe, as I just mentioned, we need to further study linearity and dry tests, the impact study. And actually, all the techniques right now has been operational now in the field program of DOTSTAR, as well as in the hurricane surveillance in Atlantic. So let me show you the results from the linearity test. So if you look at the adjoint system in any models, you can derive that if you know the theories. And all the models, let me just take an example by only showing the adiabatic energy conversion term right here. So that's showing that how the temperature change in response to the adiabatic vertical motion, where We know that, right? For adiabatic motion, if you have upward motion, you have the cooling. So in this particular example, this is the nonlinear model, and if you derive it into the basic state and the perturbation, you got the tangent linear model. And then you can write the adjoint codes to derive this in this form. Of course, in this case, it is originally, this code were written by Xiaolei Zhou at NCAR. And of course, anyone, if you learn, you can also write your own code for any simple systems. But this one is very complicated. So the blue part here shows all the basic state. That is the part associated with the forward integration of the moist version of the nonlinear model. But from here to here, we have a tangent linear assumption. From here to here, we neglect the moist physics, so dry assumption. And we have to prove that whether they might affect the results. If these assumptions have serious flaws that affects our results, then our results are simply useless. And so we have to demonstrate that in a very carefully written paper. So to do that, you do the linearity test. So with these 2 points I mentioned earlier. So let me demonstrate to you some part of the highlight of the results. First, we put 1 meter per second wind perturbation only at one single grid point. Right here, that's where we have the high perturbation, high sensitivity. And let it evolve in time. U and V involved in time. So these are the evolution of the perturbation from the tangent linear model. On the other hand, you can also test the assumption by running the nonlinear model. You run 2 nonlinear models, one with the same basic state, the other one with the basic state plus the tiny single perturbation, and you subtract the 2. So you compare the 2 to show how good your linear approximation can be. And it can be shown right here. Actually, up to 2 days, the linear assumptions are nearly perfect in this example. So this is showing the first state approximation is very valid. Of course, we can only say for this particular case. However, we can demonstrate that it is also true for some other cases we have studied. And why so? Well, we believe that because the hurricanes are mainly controlled by large-scale flow. And those large-scale flow within a reasonably short time scale, the synaptic time scale, it doesn't vary strongly, so it can be valid. But then next is more interesting. Oh, okay, I'm sorry. And we have also, of course, done more study by allowing the perturbations at multi-points and at multi-levels and at with larger perturbation, not only 1 meter per second. And we see the similar results. And this is another figure showing another interesting results. Actually, if you look at the results very carefully, the perturbation actually, they grow and propagate in time eventually into the targeted, the verification region for the sensitive case. But for another perturbation that starts from the unsensitive region, from the ADSSV perspective, it grows, it still grows, but it never gets into this verification region. So it doesn't affect the steering flow. So these are very good examples of showing how the ADSSV consistently pick up the sensitivity information from the model. So finally, we can also use the dry test to show that if you only run the model, even the basic state is dry. And the track slightly different, but in general, in a similar, consistent direction. And the results of the sensitivity based on the dry basic state and the moist basic state are identical, except the magnitudes weaker. But these are all relative terms, so the patterns are exactly the same. So what we are saying that here is that we believe that the moist physics is not playing very critical roles in controlling the large-scale flow field for the time scale we are concerned here. So let me do one more. I'm sorry for the overtime. One more example of the impact study, because this one is also very, very striking. So how do we verify these techniques or this theory? Basically, we know that there are studies about the binary interaction. Two tropical cyclones, they tend to interact with each other by rotating each other cyclonically. And this is the one example I studied before. I'm sorry, did I pass by? Oh, this is the example happened in 2002 that Fengsen hurricane and the Fenghuang typhoon, they interact with each other. And you can tell from this diagram that this typhoon is stronger, so they affect this storm more strongly. This storm, on the other hand, is weaker, so they affect this storm less strongly. So in other words, we call this in this paper, this is one kind of one-way interaction. One typhoon affecting the other one is acting less influence on the other weaker one has less influence on the stronger one. So if our theory is correct, the information can probably be picked up from this ADSSB. So let me show you the results of the calculation. So the results here are showing that if we look at the sensitivity of the steering flow on this typhoon, we see that this tropical cyclone has very high sensitivity to this storm. On the other hand, this typhoon has almost no sensitivity to this typhoon. The track of this typhoon is predominantly affected by the wind field, further north, not here. So this is a very peculiar examination of the results. Of course, I'm only showing you the highlights here. And you can also look at the vertical structure of the whole thing. And in this particular example, this typhoon is affecting this one, and you can see the whole sensitivity extends from the ground all the way up to 400 hectare. So that's the information of the typhoon. It starts from the ground all the way up. But this one, its sensitivity with respect to this radius from when I open it up is in the upper. So it is the upper troposphere flow that is driving this hurricane. So this one has no less impact. So this is another very interesting study. So finally, recently I've been working with a number of people like the Etherton and Magenta and Reynolds, and to have a comprehensive comparison of all different techniques. And I'm working on a new work together with these few guys to examine how different all different techniques show and what make more sense. And these are ways to be further studied. So let me finally talk about some of the ideas I learned from and I recommended from the IWTC. And when I gave this review talk, I talked about there are actually, I have to be fair, drop wind storm data is not everything, and it is very expensive. But the key is none of the data can stand alone. There are other important data available as well. And today I've been mainly focused on the drop wind storm targeting. But there is very considerable scope of other data being studied, especially from satellites. So Professor Liu came in the right time. Satellites, and it has been shown by various studies that these different type of satellite data are having impacts to the hurricanes. However, remember, probably I can say that only the drop wind storm so far can produce the reliable wind data, but which is very crucial for hurricane forecasting. Because in the tropics, wind is more important because of the dynamic adjustment. Wind is more important than the mass field. But it doesn't mean that the moisture or temperature field is unimportant, but it's just relatively less important. However, there have been studies to demonstrate that satellite data also need to be looked at. So the optimum combination of all these data are very important. Excuse me. And But talking about the satellite data, there has been a very huge issue about satellite data thinning because the satellite data are so huge. The volume are so huge to be digested, well digested in our current modeling or data assimilation system. So we had to do more study to look at what subsets of the data from the satellite are necessary for assimilation. This is not a very simple work. We don't assimilate everything. We want to assimilate some useful data we believe that can produce positive feedback. And that has to be identified. We don't know exactly what they are yet. At least not completely yet. And so what are the optimum variables and also optimum combinations of all different variables from different instruments we need to do to improve for observation, to improve the tropical cyclone study. There are many of the recommendations from IWPC 6, but I want to tell you that the targeted observation has been identified as a very positive, significant impact in reducing the track forecast errors, including in the Northwestern Pacific. And the IWPC 6, they recognize that this issue is very promising. But they also recommend that we need to increase the targeted observation and expansion of the aircraft targeting based on the WMO support. But of course, fortunately, even though we are not WMO member, we got it started by ourselves, and it is making some impact already. And there are also talks about how to define the best way to do the targeted observation. And also, and I'm sorry that finally, maybe this point is more important. A lot of observing system experiments need to be done before taking any new observation. And like Professor Chin Yong Huang here and myself, we have all been working on this very similar problems. So in 2008, the WMO is sponsoring this program. It's called OPEX Park. And with many different countries contributing to different components of the new observation and for the tropical cyclone study in the Western Pacific area. And that is an opportunity for many of us. But some of the colleagues in Taiwan are also proposing some so-called local rainstorm or south flow experiment in these areas. So with all these, there might be some very exciting programs to be shown in 2008. So let me finally summarize. Today, I hope I can convey the message clearly to some of the students here who are not familiar with these issues. I gave you a very simple overview of the droplet sound problem in DOTSTAR. I talked about what targeted observations are, and the theories and the backgrounds and results of the ABSSV I developed. And then I show the results based on the linearity, dry test, impact study, and how they get into the operation, and a thorough comparisons. And in the end, I briefly touch upon the recommendations, especially about the importance of other data as well. So I'll stop here. Thank you.
Okay. Thank you very much, Professor, for wonderful presentations. So you have heard all the wonderful work, which is quite remarkable. Now, please have your questions. Yes. Question one, please.
I just have two questions. The first one, maybe you haven't started. Is you define the new response function, and I think it's better. Have you ever compared with the old one? People use energy to define the.
Oh yeah.
So is it better?
You cannot say which is better because you need to do very careful study, and that is exactly what I propose to do after this meeting. So this is one case for Mary, and in this particular case, actually it happened that the single vector products from the NOGATs, they are showing high sensitivity right here to the northeast of the storm. And the black dot here shows exactly the location where we deploy the dropping sound in DOTSTAR. But there's another high sensitivity right here. But in my case, we have this part is very well matching this part, but not this part. So, but on the other hand, the ETKF is showing high sensitivity in the center of the storm, but with more, you see, when they have more colors here showing this high sensitivity in these areas as well. So actually all the cases are showing, they agree very well in this area, but not this area. But the next is, how do you do the verification, which makes more sense? Actually, that is very difficult. So we have to, because you cannot compare apples with oranges. Why? Because each data assimilation system is based on different model dynamics. So there is some fundamental difference between the models already. Second, even the other conditions remain the same. If you, for example, because if you use this, actually we can use the data to see the impacts of this data to the no-guess model. However, the increment in the initialization has something to do with the original analysis from the model. So if the model originally was able to very well, the background gas was already very good in those sensitive regions, then no matter how better observation you take, there is no use. So the situation can vary from models to models. So that makes the comparison very difficult. So what can we do next? There's at least one thing. That's the plan. I'm going to implement the ADSSB into the no-guess model. So I'm going to use the same model to do the same calculation. One on ADSSB, one about SP. Because all went into the same modeling dynamics, so we can have a fair comparison. But you cannot look at the results from simply one case because it can be misleading. And we need to show more cases. And that is why we have this new work coming out, which we are working on this right now. We have studied about 66 cases of the tropical cyclones in 2006, and to make all the comparisons, but based on different models. That's the first stage. And then the next stage is, I'm going to implement the idea into this no-guess model. Then we can at least compare the singular vector and Adjoint because they both are dynamic-based model. So it's easier to compare these two first. And it's actually, the question you asked is actually recommended in the IWPC 6 meeting that we need to identify which is a better targeted observation techniques or theories. And actually, there is no perfect theory yet. But from my own feeling, I think the definition based on the total energy will not necessarily give you the sensitivity to a hurricane track. That's my intuition. And I'm going to share more of that. So sorry. First question, and there's another one.
Second one is the whole process when you decide your box, where to put your box, you believe your model is doing a good job.
Oh, exactly.
If you say model, say it's the reality, the hurricane is going to the totally wrong direction, then you screw up everything.
Exactly.
And you can increase your box, but you will increase your sensitivity area, then you will have a problem to determine where to draw sound.
Exactly. For the model's purpose, you have to use the forecast storm center as the verification region. That is always the case being done in any type of schemes. You have to assume you trust the model first and see what result you get from that. Then, of course, you have to see if it's not true, then how much variation that might be. So in the two cases I show here, and actually they have been the tracks are basically very well. The 36-hour track forecasts are basically in reasonable errors. Yeah. But if it's in large errors, then you may say, well, can you trust that? You're right. Yeah.
Chairman.
I have 3 questions.
谢谢.
Can I speak Chinese, please? Anissa, you got to ask one question, okay? So the student can also ask a question.
Yes, you
我想问一下，就是你的 sensitivity 是相对于某一个给定的初始条件。
我们基本上就是 you decide the initial time. So the sensitivity would be you make a forecast of that model for 2 days later or 1.5 days later. You want to know the sensitivity of the track 2 days later, sensitive to the initial condition at this
Yeah.
initial
But
time.
if somebody else use another set of initial condition, he will get a different results.
Oh yes, of course. That's exactly they evolve with the model. So in different blue patterns, you might get different sensitivity. So if the sensitivity is always a certain specific location, life will be much easier because you know where to target.
Then which one we should trust?
Oh no,
For different people using different initial condition, they will get different sensitivity results.
Let me get back to that. For every initial time, there's only one initial analysis. So based on that analysis, you run the model, you find the sensitivity. So you decide where to deploy your new data to get the new data. So there is no problem about that. But for different time, you have different sensitivity region. So you want to deploy a different region. But your question might be related to, but if the different models are showing sensitivities at the same time, but at different regions, what can we do? And that actually happened. So we have to make an assessment about which sensitivity products we trust more about. So, and because given the basic understanding is that as long if all the different techniques are showing similar sensitivity patterns, you get much higher confidence about the locations where you want to try. But if they are in they are in disagreement, then of course you lose the confidence. Actually, the impact becomes smaller in those cases statistically.
还有你那个 vector， 你是用 vector 的长度来代表它 sensitivity。
the magnitude.
OK， 那所以现在如果有一个 R1， 它代表 U 影响最大。那如果有 R2， 是有 R2 的话，代表 B 影响最大，或者是 R1、R2 都有，但是长度一样，代表两个都有被影响到。就是同样的长度的一个 vector。
因为 hurricane motion 是一个 vector。
那现在如果有3个点，它长度3个向量长度是一样，但是方向不一样，一个是水平的，一个是东西，一个是南北，一个是45度的。那你觉得要丢哪一个
？No， 这个长度是决定 这个 magnitude shows the uncertainty of the steering flow. So so wherever you see the high uncertainty, longer vector, you deploy the data. The direction of vector only shows you physically that what change in vorticity will result in what kind of flow change in direction. And those are for physical understanding. But those are, and it's actually, I didn't have time to get into the details. But for example, in this particular case, the motion here pointing to the south here indicates if you increase the vorticity here, so you are going to, the storm will be driven toward this direction because the storm will increase the vorticity. So these are all very consistent with our understanding of dynamics. So what you want to look at is the long vector or high uncertainty. And you can have multiple high uncertainty regions. It's not necessary to have to be in one location only. And so, for example, we have been examining some cases I didn't show here today about the uncertainty of the sensitivity for the situation hurricane got stripped away by the approaching trough. In those situations, you will see the uncertainty in the upper levels and associated with the trough to the northwest. So it will be the uncertainty in totally different regimes. So it can vary from different dynamical patterns. So, but eventually it will be great to identify several major patterns for reference. So in the future we know where to target without further calculation.
Okay, the last one is you run the nonlinear model twice and you calculate the difference. And you say the result is identical to the result from the tangent linear model.
The propagation run.
Yes, but I don't think they should be identical.
No, for a very short time.
Should be very similar, but
yes,
not
of course. Well, it depends on what kind of accuracy you ask for. So we mean that it's very similar. That might be a more correct term to use in that patterns we show, which is very striking actually in this case. We show in this particular paper. I'm sorry. Yeah, and the patterns are very similar. Probably they have some slight difference, but we think that difference is very small. Yeah, sure. I'll take that identical word back. Similar is good enough.
Right. Any further questions? Right.
你那个我现在不是很清楚说，你放在那个 R 对那个波度为分离，这是怎么样idea的时候让发现到这样一个 definition work best for the response function. The most important is the response function. How you define response
其实
function?
这个是好问题。我当时在想这个问题的时候，事实上因为有人做中纬度的人是在算 DR temperature。因为其实中纬度的 frontal system they are sensitive to the temperature profile。但对台风的，当然我们已经比较了解，事实上台风的敏感，照理说矢流应该是对风是很敏感的，所以我们就算风。那事实上也有算风，算温度场。我待会再回到那一点。那可是风有 U 跟 V。就是你如果看 U 跟 V 答案还是可以看，可是就是没办法就觉得有一点麻烦，因为你变成有两个 vector 同时要看，那是 pretty tough， 就是有一点非常麻烦。那所以我们就想到说有这一个关系，那就把它 derive 出来。他觉得这个真的是还蛮有效的，因为 divergence 这个 component 是在我们大气的能量来说，对我们要看的大尺度流场是比较 less important， 所以我们就把一个 degree of freedom 就拿掉了，所以我这个答案就会看起来比较清楚。所以我们最后就只有 DR1 diverticity and DR2 diverticity as a vector， 就比较简单。那我刚刚跳一个没有回答，那 what about DR1 DR2 the temperature？ 那这一个部分我们也做了计算，它的敏感区域完全不一样。可是这个 point 是这样，它的 magnitude 呢，你们跟 DR diverticity 不能直接比，因为它们两个单位是不一样的。所以要比这个呢，我在我的 paper 里面有交代，你必须把两个东西都要 non-dimensionalize。那当你把它 non-dimensionalize 的时候，你就会发现 temperature 的 impact 几乎就很小，相对小很多。可是在物理上也可以了解，因为台风的运动比较容易受周围的 synaptic flow 的风在改变。那这个黄老师也很清楚。可是这不代表说温度完全不重要，其实有可能在某些情况之下，温度长可能也可以反映出它的重要性。可是，在我们现在建立的这个架构之下，一旦你要考虑风的时候，它就会比温度来对台风运动来的影响来的直接跟大很多，这个是可以理解的。
那就是小问题啊，就是说，刚刚那个陈老师有讲到那个，就是你这个它depend how good your model condition， 你预测你的那个刚好在那地方，所以你define那个 box。是。那如果当你 model 说预报错了，你这整个飞机都错了。当然，那不是我 point， 我是说，很多有些你科普球的那种情下的时候，你可不相信他跑到台湾这边来，但你可能相信他的比科普球那边到底是谁。是。所以你会有define那个 different time step 的 response function。可以。说不定这样也有帮助。对啊，这是好，谢谢，这个倒是值得思考。因为它会转的时候，你可能就如果你的 model 本来就没有感受到那个，比如说 trough 的靠近，所以它就从来没有 identify 那个 sensitivity， 你就不知道要去找那个，所以你有可能。可是这个部分是 for any system 都会有同样的 failure， 因为那已经 beyond your control， 因为 model 根本没有能力看到它。可是 model 只要能看到它，那这个方法就可以算出它的影响。基于那个比度力它转上来，那个 你看这个就可以很有趣，这个 A 就显示你可以看它为什么会转上来，可以对它这个转的影响之一。
Miniarity the case 事实上还有 extra 的 complexity because of the presence of Taiwan terrain。那有可能我个人的想法是，那个部分的 influence 在我们的这个比较 global model 里面不见，或者是 meso scale model，因为这个计算这个 Adjoint 有那个尤其 backward calculation 是很 expensive， 所以我们现在都是在比较 low resolution 下在跑，比如说60公里。那如果这样的情况之下，有一些局部的像台湾地形的影响，是有可能是已经被干扰了。那个部分刚好就发生在你独立的 case， 就不知道为什么 dropping sound 的 impact 就变成有正有负，这样，也就是说。不能保证每一个 data 都吃服了这铁料就一定要进药效，因为有时候我们的 global analysis 可能已经够好了，或者是它有一些 model 的问题，那就很难再改进了，呀。可是无论如何，这都是 IWTC 6最后的 recommendation 之一，就是说，虽然台风运动的问题好像是老问题，可是他们还是认为这是对很多地方来讲还是 number one issue， 还是还没有被完全解决。
Any further comments or questions? Or if not, I have 2 questions. Right. Very brief question.
I'm sorry. Yeah.
The first question is, when you did your sensitivity experiments, do you have initial typhoon vortex in it?
Oh, good question. No, in these cases, because we are running at a very low resolution, 60 kilometers. So the vortex, if we input the vortex, it's fine. It doesn't affect the results because generally we will find a sensitivity to the large scale flows. But when we have a very strong hurricane inside, if that's the case, sometimes there will be extra sensitivity near the hurricane center. Yeah. But that normally that is understandable because those are regions with the high wind. It tends to have higher sensitivity. But in these cases, we don't need to use the voltage. And there has been study in one of my students' thesis showing the impact after the vortex. It will be more perfect to have a vortex if we run it in a higher resolution.
In that case, will you still have the same regions with the same area showing the maximum sensitivity?
The major sensitivity in the 2 examples I showed earlier, to the northeast, about 600 to 800 kilometers away from the storm, that remains the same. But there will be extra small perturbation sensitivity near the storm center due to the presence of the new vortex.
The second question is, you have compared your linear models results with the non-linear models.
Yes.
And the results actually quite
for that 48 hours.
For that 48 hours simulation. But I think when we talk about the dynamic system, we know the atmosphere is actually non-linear in nature.
Yeah.
And the idea is when we try to understand the sensitivity, is basically we try to understand how important is this kind of non-linear feedback.
Yeah.
But it ends up you show the results quite similar. So does that mean that in that case, actually the non-linear feedback process or similar this kind of non-linear process is not that important, so you can have a result which is quite similar?
Probably for short-term tropical cyclone track forecast. But if you are talking about the intensity issues, that has a lot to do with the evolution of multi-scale interaction, including the eye wall, the convection, and Morse physics. For those, I'm very sure the non-linearity will be very important. But this has been, so the point we raised here actually has been consistent with some of the studies by others before about and what I showed on tropical cyclones. And also here, actually I even demonstrate the perturbation of different magnitudes. That's important. And we increase the perturbation up to 5 meters per second at not only one single grid, but like 9 or more, or 10. The more perturbation, the bigger the perturbation you add up, then you start to lose the nonlinearity because you have more perturbation relative to the basic state. And then, of course, the comparison will be even worse and worse. But the standard test will be starting from some single high location where you have a high sensitivity. You want to see whether they can really depict the signal. And if you can, that's okay. And of course, as I said, the nonlinearity will become more and more important when the perturbation patterns become larger and bigger. And that is understandable.
Any further questions you like to ask? Yes.
Yeah, just make a comment. We said that linearity and spatial maybe resolution is another
Exactly. Yeah. So we probably did not pick up the smaller scale evolution, and when that's but the key is for example, you see that in those two cases, the track prediction has been pretty accurate. Relatively, the errors are within only at 100 kilometers up to 36 hours. So that shows that even this type of resolution, and Jion must be very familiar with this. It's not that critical for track to have very high resolution. But if you are talking about the feedback of the intensity eventually to the motion, then for a longer time scale, it might affect the track. But here, normally we are concerned about only up to 2 days forecast. That's the limit of the current, what has been studied about tactile observation. Good points, yes.
Dear Professor dear Professor Julius John. Right. And I think today we are very grateful to have a professor to come to us. And as you have seen the great work, and you can understand how many hours of hard working has to be invested into showing you this something. So we must eat what he eats.
It's done by a computer, it's okay.
Okay, and okay, and we also thanks again Professor Wang. So today we are very lucky to have two very distinguished scientists. So let's thanks them.